Hello, everybody. Uh, I wanted to start out the semester going through a bit of an introduction. Now that you've watched the video about the syllabus and just sort of the minutia of the class, I wanted to start with an introduction of what is this class about? What is Astronomy 111 about? What are the themes? What are the major topics that we're going to touch on over the course of the semester? And then with the next video, then we can really start getting into the meat of the class. But what is this class about? This class you've signed up for. Hopefully, you're excited about it. I'm excited about it. I love teaching this class. And what are we going to get into? What are we talking about when we're talking about astronomy and specifically the astronomy of planets and solar systems? All right. So, what are we going to go over the course of this semester? First off, what is astronomy? Well, if you were alive 50 or so years ago, if you were looking at just sort of the definition, the dictionary definition of what is astronomy, the classical definition of astronomy is that astronomy is the study of everything beyond the Earth. All right, everything that's outside the Earth, everything that's further away from the Earth, well, that's astronomy, which is kind of silly because the Earth is a planet. Mars is a planet, Jupiter is a planet. So why would studying Earth be any different than studying any other planet? And why would we study Mars? And studying Mars, that's astronomy. But if you're studying Earth, that's geology. Nah, no, 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 right? When we're studying planets, including the Earth. When we learn about volcanoes on Earth, that tells us about volcanoes on Mars. When we learn something about the atmosphere of Jupiter, it tells us something about the atmosphere of Earth, right? The classical definition of astronomy as being only things that are really far away is incomplete now, right? The modern definition of astronomy is much more inclusive and much more grand because astronomy is the study of the universe, including ourselves, right? All planets, including the Earth, studying all stars, including our own star, the sun. Um, when you learn about the universe, you're learning about our own backyard because we're in the universe, right? We are a part of the universe trying to understand itself. And so, what we're really going to talk about this semester is we're going to talk about, well, you could call it planetary science, right? Astronomy 111 is a class about planetary science, focusing on studying planets and solar systems, both our own planet, Earth, all the planets in our solar system, all of us orbiting around the sun, but then also other planets in other planetary systems orbiting around other stars. What we're going to get into this semester is studying planets and solar systems, including our own backyard. The things that are very, very far away, and also the things that are nearby, like the ground underneath our feet. That's what we're going to be talking about this semester. All right. One of the recurring themes that we're going to get into this semester is not just what we think we know today, but how did we get here? What did we used to think about the universe? And if you were alive 1,000 years ago, this diagram here would be a map of the universe. And this is a little hard to read because it's an old woodcut and some of it's in like Middle English or something. So let me annotate this here for you. Here's the Earth, right? If you were alive 1,000 years ago, most people in the world thought that here's the Earth sitting still at the center of the universe, and everything else in the cosmos is circling around us, right? The sun, the moon, the planets, they're all circling around the Earth. And then behind the sun, the moon, and the planets, there's a sphere there's a sphere that hovers over the Earth that has all the stars and constellations painted on it, right? This isn't just a diagram. If you were alive 1,000 years ago, you thought this was literally a map of all of existence. This is literally a map of everything, the whole universe, and that everything up in the sky was just up there a few thousand miles. Here's the thing. It's kind of funny to look back at history and go, oh, the things people thought back then. Isn't that funny? But the thing to keep in mind, let's be generous here, right? People back then were not dumber than we are. And people back then were not smarter than we are. People haven't changed that much in a few thousand years. So the interesting question here is not, wow, what funny, weird things people used to think. People used to think that the whole universe was just a few thousand miles across. Yes, they did. The interesting question, though, is why? Right? Why did people used to think that the Earth was sitting still at the center of the universe? Why did everybody think that the sun and the moon go around the Earth? Right? Why did people think that all of the stars were just up there hovering over the Earth just a few thousand miles up? They were not any dumber or smarter than we are. So it's an interesting question. It's an interesting question of science as well as history to try to figure out, why did they come to that conclusion? What did they see? What evidence did they have that led them to that conclusion? And then, what did we learn? What did we learn after that? What have we learned in the last 1,000 years that made us realize, oh, the sun's not going around the Earth is going around the sun. Oh, the stars aren't thousands of miles away. Everything is much, much farther than that. But somebody didn't just come up with that out of the blue. We saw something. Somebody measured something. Somebody observed some evidence that made them realize that the shape and structure of the universe was different than they thought. And that's where it gets really interesting, because that's how you have a scientific revolution, right? Somebody saw something at some point that made them realize, oh, actually, the Earth goes around the sun, not the sun going around the Earth. And that the sun isn't a few thousand miles away. Actually, the Earth is not, right? In this diagram, people thought, oh, the Earth must be the biggest thing and everything, because why? Look at the moon, look at the stars, look at the planets, look at the sun. Okay, don't look directly at the sun, but if you look toward the sun, they look small compared to the ground underneath our feet, right? It seemed the evidence that they had, the evidence of their eyes, made them think, well, just look at the Earth. The Earth clearly is the biggest thing. At some point, somebody made a measurement or collected some evidence that made them realize, oh, actually, the Earth is pretty small, and that there are several planets in the solar system that are much bigger than the Earth, and actually the sun is much bigger than them. Eventually, we figured out how to measure distances around the solar system, and it turns out that the planets and the sun and the moon are not thousands of miles away. That, if this here's a diagram of our solar system to scale. Here's the Earth, here's the sun. That little distance right there, the distance from the Earth to the sun, is about 93 million miles. And that's just that little distance on the left side over there, right? Jupiter, Saturn, Uranus, Pluto, they're much, much farther away than that even, right? So, but they didn't just come up with that out of the blue. No, somebody didn't just dream it up out of nowhere. Somebody figured out how to measure distances to the sun and the planets, and it made them realize that these numbers get really big really fast. 93 million miles just to the sun. And at that point, A, your whole view of the universe changes, and B, these numbers get really big really fast, right? Just that little distance there is 93 million miles. So how can we make this easier to understand for ourselves? And one of the ways that we do that and we'll be hitting this theme over and over again over the course of the semester, is make up a more convenient unit system. Right? At some point, people said, "Hey, I'm tired of juggling tens of millions of miles. Why don't I just make up a new unit? I'm going to call it 1 astronomical unit." And very creative. 1 astronomical unit is what? It's the distance from the Earth to the Sun. So 1 is a much easier number to remember than 93 million. And so you're like, oh, okay, what's the distance of the Sun? 1 AU. And then if you start talking about distances to Saturn, how far away is Saturn? Oh, it's about 10 AU. Uranus is about 18 AU. 18 or 19? 18 AU, right? Neptune's about 30 AU. All right, 30 is a much easier number to juggle than tens of millions, hundreds of millions, billions of miles. Right? So these are some of the recurring themes that we're going to hit on over the course of the semester. Is how did people go from knowing less to knowing more? How do we know so much? What did we discover? What did we see? What did we observe? What did we measure that led us to realize that the universe isn't the way that we thought it was? It turns out it's different. And one of the themes we're going to hit on over the course of the semester is, wow, these numbers get huge, and it's really tiresome to juggle huge numbers over and over and over again. So isn't there an easier way for us to make isn't there an easier way to do this job? Isn't there an easier way to figure things out without having to juggle these astronomically huge numbers? And almost certainly, yes, there is. And that's something that we're going to touch on over the next week. All right. So what else are we going to get into over this semester? Well, when you look at the Earth and you look at the Moon, they're very different. They look very different. They have very different features. But one thing we've discovered over the last few decades is that despite the fact that the Earth and the Moon look really different, we have a common history. We are siblings in a certain sense, and that the Earth and the Moon have a common origin. And so when we study the Earth, we learn about the Moon. And when we land people on the Moon, or when we put a satellite or a robot on the Moon, and we study what's going on the Moon, we learn a lot about our own backyard. We learn a lot about Earth and how the Earth formed and how the Earth is evolving over time. Right? Then we're going to start jumping around to the other terrestrial planets, Mars, Venus, Mercury. And how are they different than the Earth? How are they similar to the Earth? How can studying these other rocky planets teach us about the planet we live on? And vice versa. How does what we know about the Earth tell us about all these other planets? Then we're going to jump out to the outer solar system and study the gas giants, or the Jovian planets, right? Jupiter, Saturn, Uranus, Neptune, the planets that are much bigger, but they have these thick, opaque gas atmospheres full of clouds and storms. And these planets are very different than the Earth. And yet we all formed together. We all formed at the same time, orbiting around the sun. These are the other cousin planets in our planetary family, all orbiting around the sun. There's a couple of hundred moons in our solar system, and some of them are really wild and different. And some of them are, every moon is unique in its own little way. And so studying these moons gives us a glimpse into the larger sweep of all the ways that planets and moons can happen in our solar system and presumably in the whole universe. Then things get really cool, because one of the big exciting topics that we can talk about now that we weren't able to talk about in previous generations is exoplanets. Exoplanets are the term for planets orbiting around other stars, not our sun. Planets in their own planetary systems orbiting around other stars. In the last 20 years, astronomers have discovered several thousand planets out there in the galaxy, orbiting around other stars. And some of them are, you could say, what we expected. Some of them look like the kind of planets in our solar system, and some of them are weird and exotic and a complete surprise to what we were expecting when we started hunting for planets 20, 30 years ago. And so, people have been asking these questions for 100 years, 1,000 years, uh, okay, 1,000 years might be an exaggeration, but, for a few hundred years, when people realized that our sun is a star, a few hundred years ago, when people realized, oh, our sun is not unique, right? Our sun is another star. Well, do all of those other stars in the night sky, do they have planets? And if they have planets, do they have people? Like, people have been asking these questions for a long time, and now, for the first time in history, we actually have found a lot of these planets. Not all of them, obviously, but we found a few thousand of these planets, and we can start answering these age-old questions about what is it like out there. That's one of the big topics that we're going to talk about this semester is how do you find these alien worlds? And once you've found them, how do we figure out what they're like? Are they like the planets in our solar system? Or are they weird in their own way? And the answer is sometimes yes, sometimes no. Um, and this is one of the real cutting edge topics in planetary science. And so this is one of the really exciting things that we're going to get into this semester. All right. Because when you start looking out at the nighttime sky, once you go out at night, let your eyes adjust to the dark. Let your pupils open up and soak up the faint light from all the far away stars. One thing you realize is there are billions, hundreds of billions of stars just in our Milky Way galaxy. And if with all those stars, how many planets are there? We don't know. We haven't found them all yet. We may never find all of them. There could be hundreds of billions. There could be trillions of planets out there in the galaxy. How are we going to find them all? Could they be like Earth? Could there be water and continents and cities and people and used car dealerships and reality television? Who knows, right? We haven't found that yet. But one of the things that we're going to talk about this semester is how do you find these things? And what should we be looking for to find planets and planets that might have life and planets that might have intelligent life that we could talk to one day? Right? We haven't done it yet, but what we're going to talk about this semester is how are we looking? Why do we think they could be out there? All right. One of the other themes that we're going to talk about this semester is how does science work? Right? Because the important thing to take away, one of the important things to take away from this class is, as I've been saying for the last few minutes, a scientific revolution doesn't just show up out of nowhere. Right? That any good scientific idea has to be based on something you see, something you observe, some evidence that you as a person, you as a scientific thinker, looks at the world, looks at the universe, and tries to figure out why. Why does the universe look the way that it does? That's the crux of science, right? That science is, how does science work, right? Science works by us looking at the world. We look for patterns in what we see. And if you notice, like, hey, have you ever noticed that when this happens, that always happens? Right? Have you ever noticed that you see a lightning strike and then the thunder happens after that? right? Have you ever noticed that the sun always rises in the east and sets in the west, right? Have you ever noticed that this always happens and then that always happens, right? These are patterns. Have you always happened that if you turn the burner on your stove up too hot, you burn your scrambled eggs, right? These are patterns. I'm just speaking for myself here. But 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 then you say, okay, you notice this pattern, and then you keep looking to say, well, does this pattern hold, right? Do we keep seeing this pattern? Well, I always notice that the sun rises in the east and sets in the west. What about tomorrow? Let's go look for some more patterns. Let's go see if the pattern keeps occurring. And then you try to say, well, let's try to figure out why, right? Why do these patterns happen? And if you think you've got a good explanation for why, keep looking, keep finding more evidence. The more evidence you find, the better our explanations are going to be. That's science, right? For example, right? There's always that pattern that what goes up must come down. And people for hundreds, thousands of years had tried to figure out, hey, have you ever noticed that what goes up must come down? Why is that? And when you go back through history, it's kind of entertaining to go back through history and figure out all the ways that people tried to explain why what goes up must come down. And the first person to get a good handle on it was Isaac Newton about 300 years ago. Right? Isaac Newton came up with this idea that, like, hey, I've got an idea for why what goes up must come down. I think there's this force pulling things together, and that pulls things back down to the ground, and I call this force gravity, right? Before Newton, it wasn't called gravity. It was just called, yeah, things fall down. What do you want? But Newton's idea of this gravity force worked well, right? It explains why things fall down, but it also explains why the moon goes around the earth and why the earth goes around the sun. So he came up with this idea, Newton came up with this idea for this gravitational force, and then he kept on looking for patterns. Does it still seem to work pulling the moon around the earth? Yeah, it does. Does it work with the planets going around the sun? Yeah, it sure does. Wow, this is fantastic, right? And so it worked really, really well until it didn't, right? Eventually, over a couple of hundred years, people found um, a few places in the universe, there's a few objects in the universe where gravity didn't quite seem to work the way Newton said it should. And nobody could figure out why. Nobody could figure out why, gravity works so well on the Earth. It works so well pulling the moon around the Earth. It works so well with a bunch of the other planets. But there's a few objects in the universe where, man, gravity just doesn't seem to work the way Newton's theory of gravitational force says it should. And the first person to come up with a solution was Einstein, right? Einstein said, actually, gravity doesn't actually work the way Newton says it does. I've got a new idea, Einstein said. I've got a new idea for how gravity works. I call my idea general relativity. Right? You've probably heard of Einstein's theory of relativity. Einstein's theory of relativity actually has two parts to it. One of those is called general relativity, and general relativity is essentially the name for Newton's theory of how gravity works. Sorry, Einstein's. General relativity is Einstein's theory of how gravity works. And it works better, right? Einstein's theory of gravity, quote unquote, general relativity, explains the weird gravity that you see around some other objects, the thing that Newton's theory can't explain. But Einstein's theory of gravity also works here on the Earth, right? So Einstein's theory of gravity works here on the Earth. Things fall down like they should. According to Einstein, the moon still goes around the Earth. The planets still go around the sun. Einstein's theory of gravity explains all the normal things that Newton's does, but also Einstein's theory of gravity explains the weird oddballs that Newton's theory couldn't. So it turns out Newton was actually wrong. Gravity doesn't actually work the way Newton says it does. But we had to find the pattern. We had to look for the evidence. Keep on looking. Keep on looking. Does gravity work The way Newton says it does over here? Yes. Over here? Yes. Over here? Ooh, no. And then somebody had to come along later and say, but wait, if the evidence doesn't always agree with Newton, can we come up with a better idea that has more evidence to back it up? And so it turns out Einstein was right and Newton was wrong. Einstein's theory of gravity is better than Newton's theory of gravity. But why? Is Einstein's theory of gravity better because it's new? No. Right? Whether an idea is new or old doesn't matter. An idea is good, a scientific idea is good if it has the evidence to back it up. And because Newton's theory of gravity only explains all the old evidence and not the new weirdos, and Einstein comes along with a theory that explains all the old normal stuff and the new weirdos, that means more evidence agrees with Einstein. Einstein's theory of gravity is better. I've used that word there. And here's something that comes up fairly regularly when you talk about science, right? I say theory. What is a theory, right? In everyday English, if somebody says, I have a theory, typically what they mean is, like, I have a guess. You're like, oh, well, theoretically, he. Oop, pardon me. There we go. Okay. Typically, where was I here? Sorry, I got mixed up a little bit. In everyday English, if somebody says they have a theory, typically what they think they mean, or what they mean to say is that they have a guess. They have they're going to throw out an idea here. And that's not what a theory is, right? If you're saying you're just going to throw out a guess, if you're just going to throw out an idea, that's what's called a hypothesis, right? A hypothesis is just you're throwing out a possible explanation. So that's a good place to start, right? If you think you have an explanation for why I keep burning my scrambled eggs, or why the sun rises in the east and sets in the west, right? Throw out an idea. And you say, okay, neat idea. Let's go run the experiment. Let's go test it. Let's collect the evidence. And if we go and collect the evidence, and if the evidence doesn't agree with your hypothesis, then okay, throw it out, right? Okay, my hypothesis is wrong, throw it out, let's come up with a new hypothesis, and then let's go test that. But if your experiment and if your evidence agrees with the hypothesis, then you think, ooh, okay, we might be onto something. All right, let's run the experiment again. And if the evidence agrees with your hypothesis again, great, okay, this is looking good. Let's do it again and again and again. And if you keep collecting evidence, and if you keep looking at the patterns, and if you collect this preponderance of evidence, if you collect this mountain of evidence, and if all of this evidence agrees with your hypothesis, then your hypothesis can graduate to becoming a theory. So what is a theory? A theory is not a guess. A theory is, by definition, if you have a theory is, by definition, the best idea that we have today, right? A theory is the best idea that we have today based on what? Based on the evidence, right? If all the evidence that we have agrees with me, then I've got this theory. It's the best explanation we have today. Does that mean that your theory is completely proven to be true? No. This is where it gets interesting, because a theory can never be proven to be completely true. Maybe the evidence that proves you wrong, you just haven't found yet, right? A theory, Newton had a theory of gravity, and then eventually we found the evidence that said, nope, Newton's theory doesn't work. Einstein has a theory of relativity. Einstein's theory of general relativity is the best explanation for how gravity works that we have today. But maybe the evidence that Einstein is wrong just hasn't been discovered yet, right? Tomorrow is always a new opportunity to watch the universe, look around, gather some evidence, and ask yourself again, does the evidence agree with our theories? Yes or no? There's always the chance that tomorrow I don't burn my scrambled eggs. There's always the chance that tomorrow the sun rises in the west and sets in the east. There's always the chance that tomorrow somebody sees something or somebody discovers something that no one has ever discovered before. And that evidence could be the new thing that proves that our old theories are wrong. And what happens if you find the evidence that your theory is wrong? Well, you got to go back and say, well, if my theory is disproven, then we got to come up with a new hypothesis. Right? Back to the drawing board. I mean, as if we ever leave the drawing board, right? Let's go back and let's say, can we come up with a new hypothesis? Can we come up with a new idea? One that has more evidence to support it. Right? So whenever somebody says, and people say this in everyday life, people say it all the time. Yeah, but that's just a theory. No. There's no such thing as just a theory, because if it's a theory, it is by definition the best idea that we have. Does that mean it's completely proven right? No. But it hasn't been proven wrong yet. It's the best idea we have so far. And if you think I'm wrong, if you think that my theory is wrong, great. Go find me the evidence that proves me wrong. Right? This is how science works, right? Science is not a list of facts, right? Science is not just a bunch of factoids, and if you memorize those facts, well, that's science. No, right? Science is a process. Science is a process of going and looking for the patterns and then trying to throw out a hypothesis and then experiment with that hypothesis and say, does our idea for explaining the evidence graduate to becoming a theory? Right? Science is not, I like to say, science is not a noun, it's a verb, right? Science is a process. Science works because it has rules. It has rules for saying, don't be confident in your idea unless you have a mountain of evidence to back it up. And if you think you have a theory and you think you have a great theory that explains things, when the evidence shows up that says you might be wrong, you can't just rule it out. You have to take the evidence seriously, right? Scientific ideas, the validity, the soundness of a scientific idea is only determined by the weight of the evidence that backs it up. Right? That's how we discover things in the universe. Right? The rules for science are that scientific claims require evidence. And the more extraordinary the claims, the more extraordinary the evidence has to be to back it up. Right? I could tell you that the universe is 13.8 billion years old, but why would you believe me? Just because I'm the one with the microphone, right? Just because I'm the one with the microphone recording this video, don't take my word for it that the Earth is that the universe is 13.8 billion years old. I better have some darn good evidence to back it up. And that's one of the things that we're going to talk about, is not just what do we think we know today, but what did we discover? What do we see? What evidence do we have that makes us come to that conclusion? Right? For example, we're pretty confident that the Earth and that the whole solar system is 4.5 billion years old. Did I just pluck that number out of a hat? I hope not, right? But one of the things we're going to talk about this semester is, where do these numbers come from? How do we get the age of the Earth, the Moon, the Sun, the whole universe? Right? What is do we have extraordinary evidence to make these extraordinary claims? I think so, but don't take my word for it. I'll show. We'll see where these where the evidence comes from. All right. These are all some of the big themes that we're going to hit on over the course of the semester. Right? What do we think we know today? What do we think we know today? What's the evidence and what are the theories that we have today that make us think we know how planets and solar systems work? How did we get that information? Right? Because it's not good enough. If I just told you in this semester, if I said, here's what we know today, and then the day after you end this class, somebody discovers something huge and everybody's ideas change, then we're both left out in the cold. We're both left uh, only knowing old information, and that's no good, right? How do we think we know what we think we know, right? What equipment do we have? What technologies do we have? And what theories do we have to explain what we see? And what do we see that leads us to the theories that we have, right? How did we, and then one of the other themes that we're going to hit on this semester is how did we get here, right? What did we used to think? What are the old ideas that people had? And then what did people see that led them to change their minds, to bring us to our current state of understanding? And like I said, we're going to get into some real cutting edge stuff this semester. What questions do we still have, right? This class is not just about the past and the present, it's about the future, right? What are some of the big cutting edge questions that we have about the planets in our solar system and all of these thousands of alien worlds that we're discovering out there in the galaxy, and how do we plan on solving them? Because if everything goes according to plan, knock on wood, fingers crossed, right? If everything goes according to plan, we're going to make some huge discoveries about planets and moons and solar systems over the next few years. And I want you to take part in this. I want, whether you're taking this class just for a general ed credit, fair enough, or whether you're wanting to study more astronomy after this semester, science belongs to everybody, right? Science is not just for people that hold degrees in it. We are all scientific people. We get up in the morning, open our eyes, open our ears and our noses, and see and smell and hear and feel the world the way we sense it. Our brains are constantly gobbling up evidence and trying to figure out why. That's what science is, right? By taking this class, you are now an astronomer. Congratulations. I deem you an astronomer. You can put it on your business cards. But if all goes according to plan, what we used to think got replaced by what we think today, and what we think today will be replaced by bigger and better and much cooler ideas that we discover over the next few years. And what leads us to these cooler new ideas and discoveries? The new technologies, and the new technologies that lead us to discover the new evidence, and the new evidence that leads us to newer, bigger, weirder, more awesome theories about how planets and solar systems and the universe works. These are many of the themes that we're going to hit on over the course of this semester. So, if you can't tell from the tone of my voice, I love doing this, and I'm so glad that you're here in this class. I hope you're excited. If it seems a little big and overwhelming, it's probably because I just compressed an entire semester of material into the last half an hour. So now that we've got the big broad overview, now we're ready to start from step one and get started on the first topic of the semester. So I hope you're interested. I hope you're excited. If you have any questions about the syllabus or about the overview, the introduction to the class, send me an email, come into office hours, either in person or online, and get in touch with me. Until then, I hope you have a great day. Welcome to the class. We're glad you're here.